Welcome to part 2 of resistivity. This one, previously we already looked at the, what you call this, resistivity equation, how you calculate resistance of conductors that are used in circuits. And also we look at a couple of graphs. So today we're going to look at a bunch of more examples. Some of these are a little bit more tricky, but that's why we look at them now. But before that, a refresher. I have a animation here, very cute one, about what this equation is about. So what affects resistance of a conductor? Remember three things. First thing is resistivity. So you can change that. You can reduce resistance, become very small, like literally small. But in past year questions, usually resistivity is fixed. They don't play around too much with that, but they will play a lot with the length and the area. So here length, when you increase length, resistance also get bigger because now you have to travel through a longer path with all those stuff in there that you have to fight with. Same thing if you reduce length. Wow, very short. Straight away go in, come out already. Area, yes. Area, the smaller it is, the bigger the resistance. Wow, you see this one affected very big. Oh. I have a question for you to think about. You see, resistivity, you decrease a little bit. Oh, I say, okay. Resistivity increase, your R become big a bit. This one, your R become big a bit. This one, your R become very small, very big. But then when you go small, it's like very, very small. So the range of resistance changes from area is much bigger than rho and L. Interesting. Something to do with cm squared. Anyway, give a heads up that some past year questions, they will ask you to think about the resistance if you change two things. For example, you take a wire and you stretch it. Like in chapter 9, we stretch wires, we do stuff. There oftentimes there can be two things that change. When you stretch a wire, it will get longer. It will get probably thinner as well. Okay. Sometimes the question will say the volume remain constant. Sometimes it's not. It depends. So whenever you see stretching wires in electricity, read the question very carefully. And oftentimes you'll combine with Young's modulus and things like that. Anyway, this is a quick simulation I want to show you. Give a fresh reminder. You can go play around with it. The link is in the description below. But yes, let's start off by looking at these few example questions. Also, I forgot to mention, these are the must try questions, means you don't just sit here and watch me do. You go and try it out first. Then you feel stuck, then you go to that particular question or, hop around. So the first one, make sure you try this out first. Pause the video if you have not. This first one is about a graph. Remember I mentioned stretching, right? So when a thin metal wire is stretched, reminds me of chapter 9, it becomes longer and thinner. That says it's a change in L and also a change in area or diameter lah. And then because of that, the resistance of the wire changes. Yes, we looked at that animation just now. But here's a very important tip. This is not always true for all wires. You might want to look very carefully at each question that talks about stretching. So here, the volume of the wire remains constant. Okay, so which graph is extension with resistance? So X and resistance. So if you find it hard to imagine, just draw. You have a wire. Then you pull it already, it becomes longer, but kind of thinner also. That's basically what I'm saying. And they say, how does the resistance change when you pull it out? Actually, for simplicity's sake, I'm going to make this also start from the tip. You'll see why later. So what is changing here? How we have resistance, right? Rho L over A. And hopefully you got the chance to play around with this thing. We want the relationship between R and X. So R and L, you might say, oh miss, we just do R and L. Should be a straight line graph increasing, but there's no answer. Why? Because, hang on a second. R is changing, L is changing, A is also changing. Getting longer, but then area decreasing. At different factors, they are not linear. Well, this one is linear. This one is not linear. Anyway, the problem is we have too many things changing. So we cannot just say a relationship of R with L, R with A, because both are changing. So what we could do though is substitute out some values. What do I mean by that? A is changing, and this key, volume is constant. Volume is actually the cross-section area times the length. pi r square h. Pi r square is the area, h is the length. So V equals to AL. So if I plug my A here, I get V over L. Now the purpose is to get everything only in terms of L and everything else constant. Okay, so rearrange already, then what? This will be rho L square over V. So then, now you see, rho is constant. Volume is constant, good. L is the one that's changing. So it's getting longer and longer. But look at this, we have a power. So now we can say for sure, all right, R is increasing also at a quadratic factor because of the square there, L squared. So you summarize as R something 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 proportional to L squared. Now let's look at all the other stuff. So L squared quadratic graph means not this shape and not this shape. So we're stuck with A and D, but how do you know which one to choose? The difference is the intercept. Why does the intercept matter? Because you see, originally you have some L0 original length. Then you extend some more, that's your extension. So that's all what you call change in L. So that means when your extension is 0, this is where 0 extension is, you already have some length and you already have some resistance, R. Okay, I repeat. Here, this dotted line is where extension is 0. Means your wire is not stretched. See, it's still fat and nice. But there's already some resistance there. So you see, this one, cannot be leh. It says when you didn't extend means 0 resistance. 0 resistance? No such thing. Okay, so this one is out. That leaves us with A, which is quadratic shape, yes. But also, when the extension is 0, you already have some initial resistance before you stretch it. That's more like it. Now let's look at another one, very similar also about graphs. This is about an experiment that we looked at earlier. But now they ask you to draw conclusions. What does this graph show? You see there's two wires, two different graphs, but you need to compare them now. Okay, so try this one out first before you look through the answer. Pause if you need more time, but yes, page 9, try it out. Also, sorry about the drilling today. Lots of noise in the back. Some neighbor is doing renovation, so I was waiting for them to stop, but then I was like, I can't wait anymore. I need to make videos, so whatever. Just ignore the noise. And yes, so here we have two wires. R equals to rho L over A is our MVP. And if you want to arrange this to in terms of a straight line graph, it will be R equals to, because R is our y-axis. X-axis is L, so that leaves us with rho over A as our gradient. Okay. The only different thing about these two is the gradient. So you're like, either rho is different for both metal or A is different for both metal. Wait a second, they said same material. So means rho is the same for both material. Means A is the one that's changing here. That's the difference between both material. But they have the same, same resistance, different area. So what does the graph show? There's a bunch of conclusions and you need to go through every single one of them to see which one is correct, which one is wrong. Let's see the first thing one. They talk about cross-section area. Area means we need to find gradient, miss. Yeah, so find gradient, You find gradient. I use M for my gradient. A gradient of X is what? You pick a point, calculate it. What is that? 20 over 0.6. So that's about 3.33333. Gradient of Y is, what is this one? 10 over 0.6. Oh, that's like half of it. Yep, it is half of it. So that's like 16.66666667. So this half. If you divide mx over my, you get 2, which means mx is 2 of my. So mx is 2 times more steep compared to my. So how does that relate to the area? Well, we know gradient is rho over A, right? We just wrote that here. So that means if you find gradient of x, so 1 over ax over 1 over ay, This from the gradient. Why the rho not there? Because cancel out, because it's the same. So that means I have AY over AX is also 2, the ratio. It's all based on ratio of gradients, okay? So how do you check if this conclusion is correct or not? You look at all the ratios. So this thing says, based on the ratio I just calculated, AY equals to 2, sorry, not AY, AX. Move from the AX is at 2AY. Means AX is fatter than AY. Check and see, correct or not? Sorry, I just realized a mistake. What is up with my brains and ratios today, man? AX, 2AX equals to AY. There we go. Based on the ratio, now that's correct. So here they say cross-section of X, AX is 2AY. Hey, that one wrong already, leh. That was the mistake that I made just now. I just somehow switched both. So this one is not correct. Then resistivity of X is 2 times resistivity of Y. Wait a second, we just said the resistivity is the same because same material. So this is, nah. You can make a correction and say it's supposed to be same. Okay. What else? When equal length of XY connected to battery, power X is power Y. Oh, we come to power now. P equals to IV, P, V square R and all those kind of things. Maybe correct. Because P I square R or V square R, whatever lah, P. So maybe that one correct. So we cancel out A and B first. Let's check D first. When same length are connected to a battery, parallel and series, parallel to a battery, the current in X is 2 times current in Y. Let's draw it out since these two have circuits. The first one, question C, says if you connect both in series, so draw 2 in series, this is wire X, wire Y. The power in X is 2 times the power in Y. How do you know? Check ratio again. Look at the ratio for resistance for different areas. So if you are lazy to think about numbers, can you draw pictures? So we have X, which is, you need 2 of these to equal 1 of AY. So something like that lah. So this is Y, this is X. So which one will have higher resistance? You look at it. X very narrow ma. So X will have higher resistance. Y will lower resistance. So they are saying when they connect, power in X is bigger because it's 2 times of Y. Power in X bigger? Yep. Higher resistance also means more power will be, more energy will be dissipated. And so we say it's more power kind of coming out there because very high resistance ma. So yeah, this one looks correct. Power in X is 2 times of Y. Wow, X very big power. I have a hint that this is the answer C. But let's also check D, just in case. You never know. No more space already, so I'm just gonna draw on the top right, on top there. In parallel to a battery. It's a good revision of circuits, by the way, just like all kinds of stuff in one question. Normally during exam, no need to do so long on one question lah, but I'm just doing step by step so you can see every single option. Parallel to a battery, we have X and we have Y. The current in X is 2 times the current in Y. Oh, current. Ooh, we need to think of that now. So just now we already say X got higher R, Y got lower R. So current how? So that means the higher resistant one will have lower current. Because more resistance, so you cannot, there's not as much current going through there. But then the one with lower R will have a higher current through it. Probably, well, as you can guess, it's 2 times. This is the cheating way if you don't want to calculate everything one by one. Okay, what they say, current in X is bigger than current in Y because 2 times of Y. Let's see. Current in X is lower than I, so nope, that's not correct. So that leaves us with C. Confirm is C. Okay, when a lot of students will make mistake when they see this, they just straight away, I will miss too many things to think about. I just see which one I like, I choose that. No, you need to think about each case carefully and see which one is not very correct. All right, let's look at another one about current ratios. Back to ratios. Here, the next question on ratios on page 13. This is a kind of an older past year question, but it's a good one because it's draw a picture for you, so you can literally see this. Now, try this one very quickly. Also, try to see what you think should be the answer if you have not tried this one out yet. Pause if you need more time, as usual. And we'll go through this together. Okay. Two wires, same material again. Ooh, same material. Whenever you see this, you can just smile and wave at it. I like it. More constants, better. Makes our life easier. Connected to the same electric supply, P has twice the length of Q. Wow. And 1/3 the length of diameter. Well, they write here 3D. Okay, good. They write everything labeled for us. It is so nice. Oh my goodness. What is the ratio of the current in P and the current in Q? So the ratio depends on their resistance, right? Resistance 1, resistance 2. I don't know what that is. But the current will divide accordingly. Here we'll have some different current. Here we'll have some different current. Just by looking at the picture alone, which one you think will have more current? You see the short, the fat one? This one will have more current flowing through it because probably more lower, more I. Because the resistance is likely smaller here. So I'm just going to write here smaller. And like Miss can look at picture and guess like that one. Can? Why not? R is larger here. And then so you have R larger. Yeah. So smaller I. Let's put that up. Let's put our educated guess there. Might as well. Now we actually have to calculate a number. So first things first, yes, you need to remember your R equals to rho L over A. And you know all this diameter thing, yes. But also you need to know Ohm's law because we are looking at current, ratio of current. So we need to find what is IP, what is IQ, and then only divide both. So whenever you see ratio, that's what you do. You find the top, find the bottom, divide both. So we need to rearrange this. So R I sub in will be V over I equals to rho L over A. So if I want V, current, let's rearrange for current. So current rearranged will be AV over rho L. That's it. Then now we need to plug in everything we know about IP and IQ. I'm going to do the shortcut since we already did the long way in the previous video, the paper 2 one, the ratio everywhere one. So the shortcut is, among all these variables, A, V, rho L, which one is constant? Put a box on it. Lock already, cannot change. A is changing because of diameter. V is potential difference. It's actually the same for both. Constant for both. Why? Because here you have some V coming from a power supply. And because these are parallel lines, the V across here to here for any parallel line is the same. So the potential difference across P is the same. Equals to VQ, same. So V is the same for both laws, so eventually they will cancel out. Rho, same material, yes, so it's the same. So what's changing is A and L only lor. Good, I like. So let's divide IP over IQ to find the ratio. Now the rest constants, they will just cancel out top and bottom. So what's left is area of P over length of P, and then area of Q over length of Q. I rearrange a bit. APLQ, and then down there will be AQLP. There. Area have to pi r squared d, right? Pi r squared d. Sorry, pi r squared or pi d squared over 4. So I just leave the d lah, because all the rest are just constants. So that's left with that. These are shortcuts. D squared LP. Now we plug in everything we know. Yes, now we do that. What is dP? The diameter of P is just D. So just D squared. Length of Q is L, the curly L, so you just L. Diameter of Q, 3D squared, so 3D squared. And the length of P is quite long, 2L. Then you just see what else you can cancel out. So here L and L are just symbols already. So L and L can cancel off. They are not variables anymore. d square and d square can cancel out. So what's left is 1 over, green color, 1 over 339, 3 square times 2. That will be 1 over 9 times 2, 18. So 18. Ta-da! That's how you can find that thing. So yes, you can shortcut by this as long as you know what is constant, because if they're constant means you can cancel out the top and the bottom. If they're not constant, then you need to find what values to plug in. Alright, so that's current ratios, just to top up on last video's ratio calculations. Now we go to graphs. Actually, I changed my mind. The glass graph that we're going to look at is quite mind-boggling if you're not sure what to think about it. So we're going to look at a conceptual question first. It's the wrong page. Let me find page 17. 14, 15, 16, 17. There, page 17, ON13 P13. This is, page 17. This is a very, very good conceptual question that will kind of catch any misconceptions you may have about wires and, how to use ideas about it. Okay, so read through, take a guess. Again, these are the must-try questions, so I want you to be active in trying them out. Instead of just watching the video and just like, okay, understand this, then you do yourself, don't know how to do. So let's see. Hopefully you have finished trying out the question also. Pause if you need more time. But here, you have an electric current going through a very funny shaped wire. See, got section one. The middle like a bit thin, the outside a bit thick. So you have a thick copper wire, thinner copper wire, and then go thick again. A current flowing through. Which statement about the current and the speed of electrons? Current I, electron is like the drift velocity kind of thing, V. What is true in the wires? Let's write this below. Let's go through these one by one. The current and the speed are less than in the thicker copper wire. I'm going to rewind a bit and say, hang on a second. Before this, when you draw circuits, right? Let's say this is part of a circuit. We always say the current go in here is the same as current exiting. What if got different size? Different size, also same thing. This current here is the same as this current here, is the same as this current here, is the same as, you get the point. Same current. So here they say current are less than in the thinner, thicker. No, current is the same. Okay, this one says same. Okay, maybe B. Current same. Maybe. Current same, maybe. Okay, so A is out of the picture. So we know current, it has to be the same. Now what about the speed of electrons? This one we have to borrow an earlier equation from Nave, the very, very first video. How you calculate current in a conductor. See, we got resistivity in conductor. We have current in conductor. Wow. You hopefully know your conductors pretty well now. So we have NAVE. V is the speed of electrons flying through this wire. So all this dot here, all flying. V will be I over NAE. In all these things, what is constant? When you go from the fat to the thin to the thick wire, current is the same through the whole thing. Yes, we know that. N depends on the material. All copper. First one copper, second one copper. Okay, so N is the same for everything. E is of course the same, it's a constant, the 1.6 times 10 negative 19. So what's changing here is A is changing. So what that means is V is proportional to 1 over A. What does that mean? That means whatever has a bigger area, you have a slower speed. So big area means slow speed. Or if you have a small area, big speed. Means the electrons are kind of like, on average, moving faster. Wow, this may be counterintuitive for some of us because we think of current I as how fast they're moving. Well, yeah, it's kind of how fast they're moving, but also you want to look at the drift velocity of each electron. So now with this idea, okay, so if your area is very big or like this one, moving slowly, so V is quite small, it's smaller. Okay, here also V is smaller velocity, speed of electrons, I should say. Then in the middle, when it's very narrow, the electrons have to move pretty fast to get through it. So your V here is larger. They have to like, I also narrow, faster go. If not, behind cannot. There are traffic jams, so they have kind of to move faster in that narrow space. So what do you have? So this one, electron speed, electrons not the same anymore. So B is out. Bam. C says what? Current same. Okay, we already established that. Speed of electrons in the thinner wire is greater than. Oh yeah, thinner wire, larger. Yep, that's correct. Sounds right. Check the last one just in case. Current same, yes. Speed of electron in the thinner wire is less than. Now we can't think of that one. C is this one. Okay, this is a misconception question. Oh, thin, very thin, narrow, and then, how come they are moving faster? Because they need to faster move, ma. Think of a pipe. You have a water pipe, same amount of water coming in per minute. That's like the current, water current, same amount coming in. So when they're in the big pipe, they move pretty slowly. But if they're in a small pipe, they're all squashed in there, so they move pretty fast in a small pipe. Then they go to a big pipe again, they're very chill. Yeah. Okay, now let's go to the final question on the diameter cone graph. On page 14. This question is kind of a build-up of what we have done in the previous video. Remember, we looked at zero potential and then what's the current drop. Very similar, but now it's a cone shape. If you don't know what I'm talking about, go review the old video a bit, because this will build on that knowledge. But I'm going to teach you some neat tricks. Anyway, let's see. We have a cone shape, very funny shape material with different diameter. And then there's a current going in, current going out. It should be the same. You should know by now the current flowing through the whole thing is the same. The narrow end of the wire is where we say potential of zero. So here, I mean, they put it further out, but yeah, you can say here is where zero is. So you're going to start off with some V. You take the voltmeter, you measure between the 0 and that V point, and then you go smaller, 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 smaller. This way, smaller, 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 smaller. What do you measure? That's all the graphs here. Okay, so let's go through one by one and try to logic them out of the picture. The first one, A. Same voltage and then suddenly drop. Cannot be lah. We already established that earlier. There's no such thing as voltage suddenly same throughout the whole conductor and suddenly drop. No. B would be correct if your conductor is not the shape of a cone. So if your conductor was shaped round like this, uniform area, then yeah, as you go along, you have a slower and lower potential until eventually you reach zero. So yeah, this is not correct in this case. It would be for this kind of conductor though. Then we are left with two choices. This curvy one or this curvy one. Both also curvy. How you know which one? This is where if you try out some equation stuff, you will probably get quite stuck. You're like, the equation's not telling me anything. How do I go from here? So we're going to try to think of a different way, a trick to help us understand this better. Okay, so rewind a bit. Remember I said the uniform one, right? Okay, for every section here, let's say a small section, change in length. Let's say here is x0 lah, start of the axis. For every little section that you go, you will have a drop in potential. Am I right? Okay, for small section, small drop. Then you take the same next section, also the same change in length, also the same drop. Same. So, I just write everything lah. So throughout this entire uniform metal wire, your ratio, or I should say, the change in potential over the change in that tiny length is the same. Constant. Now, where have we seen this before? Change in something over change in something. Oh, it's a gradient. So, this is also known as the gradient. The gradient here, constant, decreasing, going down. It's the same. Okay, gradient is constant, so you have this straight line thing. But how are you going to apply the ideal to this thing up here, the curvy one? So, okay, let's try this. Make sure you have chosen the answer first. You see either it's C or D. Okay, let's start off with the top. I'm going to cut this up into equal tiny lengths, the delta x, so that all my delta x is the same. Okay, give me a second. Yeah, a bit not same already. Yeah. So each of these is a delta x. They're all the same. I purposely do it that way so I can see. Now let's look at the change in potential for each one of them. So the first one, you will have some change in potential for some tiny length. Okay, but then as you go to the next one, the resistance is a bit different already. What do I mean by that? Here the resistance is pretty small because the area is pretty big. Then the area gets smaller, resistance gets bigger. Then resistance gets bigger and bigger and bigger and so on and so forth. So each time your change in V will be a little larger. Then as you go on, change in V is a little larger. Then change in V get very big. Then here change in V is huge. Now this change in V is for each section. So what is happening here is, in summary, therefore, your change in V for each tiny little length is increasing. That's also known as an increasing gradient. Oh, so you have to look here. As you go from left to right, which one has an increasing gradient? This one is kind of like flattening out already, going to gradient 0. So, not D. The answer in this case will be C, because here you start off not so steep. Then you get, wow, very, very steep. That's because of your change in V for each tiny little section. This is the fastest way to solve this kind of question. Okay? Because if you do the equation thing, you will do, then you're like, oh my goodness, miss, so many equations. And yeah, you will save a lot of time if you do this method. So yeah, think of this another way. Change in potential for each tiny little section. How is that changing? Okay, just to top up, this one here, resistance of each section is the same. Each section resistance same, but this one, each section resistance is getting bigger and bigger because the area is bigger and bigger. Alright, so that's all for the list of tricky questions I want to show you. Hopefully that was helpful, especially this one, and some of the others will help train your skills in that. Okay, so yeah, that's all for resistivity. You're kind of done with chapter 19 as a whole. The next video will be kind of also a bonus, the next video will be a bonus video on certain specific types of resistors. They are very special and they are very specialized. But yeah, we're done with chapter 19. Next up will be chapter 20. And you will see we'll have lots of fun in chapter 20 too, because now it's circuits, but with a twist. Now it's like a puzzle. Okay, so that's all for resistivity. Go try out the homework questions to make sure you are familiarized with different kind of questions, and please post questions in the questions channel. Discuss with someone to brainstorm what the answer is. Alright, I'll see you in the next chapter.